There are many types of exponential and growth and decay applications. Compound and continuous compound interest are some that we've already looked at. Let's look at a few others. For example, bacteria tend to grow exponentially fast, so this is a good problem for exponential growth. It says the number of bacteria in a certain culture increased from 800 to 4,000 between 7 a.m. and 9 a.m. Assuming growth is exponential, the number f of t of bacteria t hours after 7 a.m. is given by the formula f of t equals 800 times 5 to the exponent t over 2. Okay, a couple of things I'd like to point out. T hours after 7 a.m. Okay, so t hours after 7 a.m. would mean that our time marker 7 a.m. corresponds to t equals 0. Also, we began with 800 bacteria, so that's your initial amount. Now in your money applications, we just called that capital P for principal. In this case, we're going to mean something similar, but let's indicate it with a more scientific looking notation, which is P with a subscript 0, meaning the amount present at time 0. Okay, and then you see your formulas are modeled in the same fashion as the continuous growth model. In other words, it's like this. It's a number that's your initial amount times some base to a power. Okay, that's the typical exponential model, and we see that we have that here. Okay, our base is 5. All right, it says estimate the number of bacteria at 8 a.m. So the first thing I notice is that 8 a.m. corresponds to time 1 hour. So our calculation is f of 1, which is 800. It's 5 to the 1/2 power, which I actually, for WebAssign purposes, could stop here since the calc pad appears, or I could do the calculation. If I do the calculation, this is approximately how many bacteria we have accurate to 3 decimal place accuracy. Okay, but I would suggest, as far as, especially in a testing situation, that you don't spend the time to simplify or calculate. However, it does help you, sort of see the manner of growth that you have. Okay, for example, if you're already at 4,000 at 9 a.m., you should not be over 4,000 at 8 a.m. because it was earlier than 9 a.m. All right, moving on to the second part. It says estimate the number of bacteria in the culture at 10 a.m. Now, I guess I need to point this out. Yes, give your answer accurate to the nearest whole number. So in that case, we can't enter the formula like we could if it didn't say estimate. So we'll put in the answer for part A to the nearest whole number here. Okay, now back to part B. At 10 a.m., that's 3 hours after 7 a.m., so I'm calculating f of 3, which is 800. It's 5 to the power 3 over 2. Okay, and when you're doing this in a calculator, make sure you get the 3/2 in the exponent. And I have 8,944 and some change here, if you will. Okay, so accurate to the nearest whole number would be 8,944. Okay, all right, and lastly, the number of bacteria at 11 a.m. 11 a.m. It's 4 hours later. Okay, and f of 4. Similar calculation. Now in this case, your exponent's 4 over 2, so you could certainly reduce that before you do the calculation. And you see here we have 20,000 bacteria. Okay, so that's quite a bit of growth in just a very short period of time. Now, let me make a point here. If I jump from, just so you understand exponential growth, 800 to 4,000 in 2 hours, then every 2 hours I'm going to make the same relative multiplication in my final answers. Okay, so for instance, 800 times 5 is 4,000, which suggests our base 5 here every 2 hours. So essentially my bacteria is growing by a factor of 5 every 2 hours. Well, when I'm at 4 hours, that's 2 hours after the first 2 hour mark, okay, which I was at 4,000. So notice that 4,000 times 5 gives us what we think we should have.